So in this class, we are going to check how to apply the disk method and also the shell method at the same time. These are two different methods that we are going to have in the syllabus of mathematics N6, which differs to what we had in our mathematics N5. So I want us to consider the introductions that we had for mathematics N5, considering the volumes also, so that you have a basic of what is to happen or what are we going to have in actual sense. So you are going to see that in the calculation of volume, we are going to be applying these formulas that you're given here. These are the formulas that you're going to apply for the volumes. And we are going to have an explanation of these formulas, but just for the basic of understanding of these two different methods that we are going to have now in N6. All right. So we end the calculation of the volumes. So for the areas, nothing has changed. The area between the curve and the x-axis, the area between the curve and the y-axis, the area between the two given curves, everything that we had in our N5 is exactly a continuation that you're going to have in N6. So I want us to check that part, the introduction that we had in N5. So that one, we are not going to have a talk about it. We're just going to use that application in question papers just to see that, so that you see that it's one and the same thing. All right. So I was saying for the volume now, in N5, we had something like this. This is what we had, exactly something of this nature. You were given a curve. Maybe this is the curve of y is equal to f of x. Given the curve of y is equal to f of x, you were taking your limits from A to B, having the representative strip in the x-axis because of what? Because of the limits that you're given, the limits that we are having here, they best suit for x. They best suit for x. So in actual sense, what you were doing is that you were being asked to calculate the area. And I said for the area, the strip for area represents the area with respect to that strip. What am I trying to say? The strip here is for x. The representative strip is for x. Meaning to say the limits that we have in this case, they are for x. X ranging from A to B. So if you were to calculate the area, let's start with that part. The area was going to be with respect to x because the strip is for x, so that you understand me there. So we're having our area as the integral of y with respect to x from A to B, where y is the function of x. Y is equal to f of x. So therefore here, we are going to substitute something that is in terms of x, maybe, I don't know what you have there. That was your area. So the area was actually something automatic to say, with respect to x, the representative strip with respect to x. All right. It was never, or we never had a condition where we are calculating an area for y with a representative strip of x. With the representative strip, that one it's not going to happen for area. It's the strip for x, the area for x. Meaning to say, if it is the area for y, we must have the strip for y. That is, we must have the limits for y. That is for area. But now, when it comes to the volume now, I want you to be careful now, because this is the difference part that we're going to see here. When it comes to the volume, you are going to be given the volume depending with what you have. Depending with what you're given, you calculate the volume depending to how you're given the volume. Is it about the x-axis? So you are given the volume from the axis of rotation. The axis of rotation is the x-axis, meaning to say we are calculating Vx. The axis of rotation is the y-axis, meaning to say we are calculating Vy. So you are going to see that whenever you are dealing with a volume and the strip there that you're given, like we're calculating the volume for x, that is the axis of revolution was for x, that is Vx. And on your diagram here, on the limits that you have on the diagram there, the limits that are corresponding there are for x. Check note. The volume you're calculating with respect to x, the limits that you're given there are for x. On that consideration, that is exactly what we had here in N5. We had a consider, just like area for x, the strip for x. That is where you use what you call the disk method. So the disk method, that is you apply when you're calculating the volume that corresponds to its strip. Meaning to say the volume for y must correspond the strip for y. That's the case of our disk method. Where whenever we talk about the strip for x, the limits for x from A to B, the strip for y, meaning to say we are referring to the limits from C to D. They're now for y. But now, considering that, it must have a strip for y, like something like this. It must correspond. For you to apply the disk method, maybe we could have function like this, taking our limits from C to D, and the strip is for y, and this will be x is equal to f of y. There you go. It's still disk method. The volume about y, the strip is for y. But once it opposes now to say that the volume that you're calculating is for y, but the strip that you have like here on our diagram here, you'll be asked to calculate the volume about the y-axis. And you're wondering how, because the strip that I'm having there is for x. It's no longer corresponding to how it's supposed to be what I'm used to. Whenever you see this case happening, that is where you use the shell method. That's your shell method there. That's your shell method. The volume with the axis that you're given of rotation does not correspond with the limits that you're given. You have the limits for x, you are calculating the volume for y. How is that possible? That is the shell method. You have the limits for y like this one. You are asked to calculate the volume for x, but given a strip for y. They're asking you to calculate the volume for x, but the strip that you have is for y. How is it possible? There, we are going to use our shell method. So it is a method that allows us to calculate the volume for y from the limits of x, which is something that we are not used to that. It allows us to calculate the volume for x from the limits of y. That is your shell method. So let me explain it this way. We are simply saying, in actual sense, you can take it this way, or you can use the concept that whenever you are to use the disk method, this part of the disk method, whenever you are to use this part of the disk method, it is on a condition that you see that at the end, it can be a condition where the representative strip is perpendicular to the axis of rotation. Like volume for x, the strip is for x. So you will see that the representative strip and the axis of rotation, they will be perpendicular to each other. So you can use that condition that the representative strip is perpendicular. So this is perpendicular, like they meet at what? At 90 degrees. Okay, let me just write, is perpendicular to the axis of rotation. So this must be perpendicular to the axis of rotation. That's the idea there. If there is a condition like, let's say for the y-axis, this one, it means if you were to use that, you were going to have something like this. Like I said, or maybe this is your C and your D. The strip that you have there is for y. This is the area that you're talking about. So if we are calculating the volume for y, the strip is for y, they are perpendicular, the strip, they are perpendicular to each other. you apply disk method. You are calculating the volume for X, the strip is for X, they are perpendicular to the ground. You apply the disk method. What about the shell method? This is opposing now to say the representative strip is supposed to be parallel. So in this case, the representative strip is parallel. Those parallel to the axis of rotation. To the axis of rotation. So that's another part that you can use if you fail to use this, but I think this is the easiest way, guys. The volume, when it does not correspond to the limits or to the strip, that's the shell method. The volume, if it corresponds to its limits, to its strip that is given there, the volume for X, the strip for X, that's the disk method. So it will further go on. Remember our volume, how do you calculate your volume, this and that, the integral of y squared when it is a disk method. So you're going to see that under the disk method, these are the formulas that you are going to have. All right, so let me indicate it this way. So these are the formulas that you are going to have under the disk method, these ones. All right, let me indicate properly here. So you are going to use these formulas under disk method. So is Vx, volume for X, the strip for X. So remember that the formula from N5 Vx, the integral of y squared. So that is the part of what? Your disk method. So this one, the volume for y, the strip for y. But now, here I want us to just make this one. Yes, here they are using A and B to represent the limits. But for y, I want us to use C and D so that we know these are two different things there. C and D for y, C and D. So we are saying these are just the limits that you're given. I think I indicated the diagram here. All right. For X, we can just say we are moving from A to B. Then for Y, we are going to use C and what? C and D as our limits. So that is for X. X is greater than or equal to A, less than or equal to B. Then for Y, the strip of Y, Y is greater than or equal to C, less than or equal to D. So these are the limits that I want you to just use the C and D. But as long as you understand, guys, that these are the limits, no problem. So where do we use this part of y1 squared minus y2 squared? Remember, that will be on a condition when you have got two functions that intersect at a certain point, and you've got a and b as your limits, just something like that. The top graph minus the bottom graph, I think that one we talked about it from our N5. That is how you're going to use this one, where you're subtracting. So this Vx, which is pi, the integral of y squared dx, that is our normal formula for volume. So that is for the disk method. Then for the shell method, these are the ones that are remaining here. Whenever you are to use the shell method, remember I said it opposes what you are given in terms of the strip. So these are the formulas that you are going to use for the shell method. All right. So Vx, the strip must be for y. As you can see, Vx, the strip is for y. It opposes, meaning to say these limits are for y. And whenever we talk about the limits for y, we are talking about the limits C and what? C and D. So there they are using A and B, which is fine. But us, we just have C and D so that we do not confuse the limits for X and those ones for Y. All right. So that is the volume for X. So you're going to use the strip for Y, meaning to say you are using the limits for Y. The volume for Y, the strip for X. So this is the formula. So let me explain this formula under the shell method. We are given that the volume for X can be written as, this is 2 pi, the integral of xy like this with respect to y. So if you're just given a single function like the function and bounded by the axis, it's fine. This is what you're going to do. So as we can see, it's with respect to y. So meaning to say this x must be in terms of y. In terms of y. So x is actually representing what? F of y, because we must integrate with respect to y. It is the same thing here. Dx, it means this y here is a function of x. X that we see here, there's nothing to be, it's just, there's no substitute there. There's no substitute for this. It's just like this y, it's already with respect to y and there's a y there. So there's nothing that you substitute because you need to integrate with respect to what? With respect to y. There with respect to x, so this x, there's nothing for this x, but this y now, it must be in terms of x so that it can be integrated in terms of what? In terms of x. So that is the idea there. So when you are now given that condition of the two functions, like let's say is between two given functions, something like this. What's going to happen in this case? The limits that you're given for x, you've got a, and you also have b here. The strip is for x. But like I said, in that case, they are not going to give us to calculate the volume for x because it is corresponding with the strip for x. So you'll be asked to calculate the volume for y. But the limits are for x. So as you can see, that's where the shell method can be used. But as you can see, Vy is, according to the actual formula, is supposed to be 2 pi y. 2 pi, the product of what? The product of x and y. This is our formula that we are having from our formula sheet, from A to B. But there are some adjustments that are supposed to be made because this is between two functions. So we are going to have this y representing y1 minus y2, the top minus the bottom. So at the end, our Vy is going to be 2 pi, the integral of x into y1 minus y2 with respect to x, whereby these are supposed to be in terms of what? In terms of x. These are functions. This one, f of x, maybe this one is your gx. They are supposed to be in terms of x. This one is already in terms of x with respect to x. So there's no substitute for that. There's no substitute for that. So that is the idea there of the shell method. We do not square like what we had under the disk method, y squared, this squared. No, it's just y1 minus y2. So it is the same thing even if the curve was given like this. So guys, I can't explain like all, if you just take the idea there of those formulas, you can answer any question. Like I can't represent all of these conditions, but if we just know that formula, we can answer any question. So it is the same thing. Let's say we had something of this nature, our limits from C to D. This time our strip is for y. So this is the representative strip for y. And we're supposed to calculate the volume generated by this solid that's going to have there. So if we are to calculate, because if it is for y like this, and you're asking to calculate the volume for y, there you're just going to use the disk method because it is corresponding. The volume for y, the strip for y. That is the disk method. But as we want a condition where we are using the shell method. So for the shell method to be applied, they are going to ask you to calculate the volume for x. Whereas the limits that you have there, they are for y. They do not correspond. So it means we are back to the shell method. So meaning to say you were going to take the formula under the shell method. As you can see, under the shell method, you have to make adjustments. They did good on the disk method. They gave us proper formulas. Even if you're given two curves, you use these formulas. But on the shell method, they just gave us a general formula. It is you who is supposed to make adjustments when you are given this formula. So we saw that the formula to calculate Vx, which is under the shell method, which is this one, is going to be given as 2 pi, the integral from c to d of xy with respect to y. Like I said, these are just limits. You can use yes, a and b in your understanding that they represent the limits for y. What I want you to understand that it's different from a, b, this one. These are the limits for x if you are using this a, b. So I want us to be careful on that one. So meaning to say here, it was supposed to be like this, but remember, these are functions in terms of y. This is your x1, which is in terms of y here. This is your x2 in terms of what? In terms of y. The top minus the bottom. So what it means is that we are supposed to make adjustments on our formula now. Is going to be the integral of the x that we are supposed to have is now the difference that we have, which is x1 minus x2, the top minus the bottom. So we are going to have this as y into x1 minus x2 with respect to y, where these are functions that are different, but in terms of what? In terms of y. That's it. So it can be integrated in terms of what? In terms of y. So what you need is the presentation first. The presentation that you have is going to actually give you the exact formula to be used. So I do not know, guys, but that is what you're going to need. So let's conclude this and say, whenever the strip is corresponding to the volume of axis, or whenever the volume that we are given there corresponds to the strip that you are given or to the limits that you are given, there you use the method referred to as the disk method, which uses these formulas. If the volume is for y, but the strip is for x, or the limits are for x, the volume about a certain revolution does not correspond to the limits or to the axis, or to the strip that you're given does not correspond to the strip. That's where the shell method is used, and these are the formulas. You're calculating the volume for x, but the strip or the limits are for y. Shell method. And these are the formulas, and these are the adjustments for the shell method, because for the disk method, we are used to that, and also the formulas are properly presented. So that's why I made further formulas. Still, under the shell method, we can have a condition where the two functions are, we have got two functions that we are given. So that is the idea there. The strip for x, the volume for y, that's shell method. The strip for x, the volume for y. The strip is for y, the volume is for x, but there are two functions, you have to subtract them. The formula is still the same, but you make adjustments on your formula. That's it. So I want us to check these typical questions that you're given, and we'll be able to differentiate these methods. There we are given, determine the volume, take note. Determine the volume of the solid generated when the area between, so as we are going to have a diagram showing the area, this rotation thing, something there. So it's between the curve, this one, and the x-axis rotates about. So this is the major idea, guys. What we are having here is not affecting our diagram. When you read this information, please do the best of yourself. Leave this one. You see it later. This one. Don't look at that. Don't look at that. So read this information on its own. Understand this on its own. Just understand that on its own. All right. So we need to have a curve of y is equal to 3x minus x squared. It's a quadratic function. It's a negative there. As we know, if we get given a negative, we're going to have a function of this, which is a Z shape. but we need the x-intercepts in that case. So you're going to need the x-intercepts. Remember, if y is equal to 0, that means this will be 3x minus x squared is equal to 0. Factor out x, the common factor, going to remain with 3 minus x squared, and this, that's x is equal to 0. So one of these must be 0. So it means x is a 0, or this bracket must be equal to 0. So if 3 minus x is equal to 0, just going to take x this side. So 3 is equal to what? 3 is equal to x, or x is equal to 3. So these are the x-intercepts. All right, x at 0 and x at 3. Then for the y-intercept, we understand that x must be equal to 0 there. And if x is equal to 0, it means y is also a 0, if we substitute as 0. So that means the y-intercept is at 0, the x are at 0 and 3. And also we talked about the shape that this is a negative. So we are going to have a set shape at the end, something like this. So the sketching part of our graph, like I said, is something else that is not about the two questions that follows there. Let's sketch. Let's not worry about those questions. No. So this is what you're going to have. This is just a sketch here. So you are going to have properly your x and y axis presented. All right, so this is our x-axis or y-axis like that. With the x-axis, as we can see, the major points that we need, the y-intercept is at 0. This is where it is. And also, that's where also the x-intercept is. It's also at 0 here. All right. The other x-intercept is at what? At 3. So it's just like 0, 1, 2, 3. So as you can see, and also the shape that we have, a set shape like that. So you see that our function at the end was going to be something like this. All right. So we were going to have something of this nature at the end. All right. So like I said, guys, this is just a sketch. So with this sketch that we are having, the question is, guys, do not consider this. Yeah. They are saying determine the volume of the solid generated when the area between the curve and the x-axis rotates about. So the area is supposed to be between the curve and the x. This is the major part. Let's look at where the area is supposed. The area that we are going to rotate is between where? The curve and the x-axis. This is our x-axis, this one. And this is our curve. So which region is bounded in between where we see the curve and the x, in between the curve, in between? We are going to see that the region that we are talking about is this one, in between the curve and the x-axis. This is the region that we're going to talk about here. Bounded by the curve and the x-axis. This is the region where the area is supposed to be calculated. So the question is, in this region that we have represented right now, where do we have the limits? Which limits are we given on this function? As you can see, it's bounded here. This is the boundary of the region, this one. That's your boundary. So in this boundary, do we have limits? Yes, we have. And these limits are for x. From this point up to this point, that is where it is bounded. The limits are for x. So it means, according to this diagram, it is best to have the representative strip for x. So as you can see, guys, I am drawing this representative strip, not even checking the question that is following. Why? Because adjustments can be made on those volumes. They must follow the strip. Volume, it follows the strip that you are given. You don't force the strip to follow the volume. To say, they are saying, calculate the volume about the y-axis. You force this strip to be under the y-axis. Like, no, that one is only for area. And they will give you proper condition. Volume, it follows the strip. If it is the strip for x, this volume, it will follow that strip. Don't worry about it. indicate your diagram properly, not checking to say, what are they saying? They are saying the volume is supposed to be rotated about the x-axis or about, don't check that. Check your diagram. What do you have on your diagram? Is the information complete? And where can you put the limits? We do not have anything for y here. There are no limits for y. This is the best presentation that we can have. So according to this, now we have to go back to our diagram. All right, our question now. Y is equal to 3x minus x squared. That was our question. So the strip is for x because the limits are for x. Our x is taken. Remember, I said x ranges from A to B, where our x in this case is taken from 0 to 3. All right. So our x is taken from 0 to 3. That's where the limits. Why we can't say y is from here to, we do not have the limits there. We have to find maximum point, which a lot that you have to consider there. Use what you already have on your diagram. So this is it, guys. This is our sketch. This is our diagram. So let's answer the question now. The question is, determine the volume when all this that we have indicated on the diagram rotates about what? The first question, about the x-axis. So that one, you'll see it later on. It's not something that you're supposed to consider. So to rotate about the x-axis, it means you have to calculate what? Vx. To rotate about the y-axis, it means we have to calculate what? Vy. These are now volumes in this axis, Vx. Volume in this axis, Vy. So let's start with the Vx, which is our first question. So our first question there, which is our A, is to calculate Vx. So this is what I said. Volume, it follows the strip. So don't worry about the volume, the strip. When you are drawing this, to say you'll be checking what is the question about. No, the question for volume, it follows the strip that you be given. So don't worry about that. So here, the volume that you're given to be asked to, that you're asked to calculate is the volume for x. And what are we given in terms of the strip? The strip is for x, meaning to say I talk about the limits for x. Which method do we use? Where the volume and the strip, they correspond to each other. We say that one is the disk method. We are back here. The volume that you are calculating is for x, and also the strip is for x. There's no way. Here's the disk method here. The volume for x, the strip for x, the volume for y, the strip, they correspond, they go hand in hand. You use the disk method. The volume and the representative strip, they are corresponding. The volume and the limits, they are corresponding. So meaning to say, in this case, we are going to use the normal method, which is our disk method. The disk method is the normal method that we are used to from our N5, where the volume and its strip, they are together, they are corresponding. So remember, in our N5, we said Vx is simply the integral of pi. We've got our formula, which is pi, the y squared. So Vx, we're going to take this formula here. Remember, these are the formulas for disk method. So you're going to take this one. Vx is equal to what? Pi, the integral of y squared dx. So that is the best formula that you're going to have there. I hope this one, we are clear about this one, guys. This is your basic that you are used. So it's going to be pi, the integral of y squared dx from a to b, the limits of x. So that's it. So Vx is going to be pi, the integral y squared. This is a function of x that your function of y that you're given in terms of x, which is f of x, this one. Then a and b, these are the limits in between the graph and the axis and the x-axis as we are given. So we said the limits are from 0 to 3. So that is the lower limit from 0, upper limit 3. Then y squared, remember y is 3x minus x squared. So this is 3x minus x squared, but this is supposed to be squared. With respect to x, we're going to have our volume. So that is the idea there. So the question is, after that, as long you've got your formula, this part of the integral, the expansion of these brackets, guys, that one is up to you. How do you expand? I talked about the expansion of a minus b. You can open two brackets. It's up to you, guys, this expansion. So 3x and 3x, that will be 9x squared, 3x and this, that will be minus 3x cubed, minus x squared multiplies 3x, that will be minus 3x cubed, minus x squared, and minus x squared, that will be a plus x to the exponent of a 4. You add those exponents. So that means here we're going to have 9x squared minus 6x cubed minus 6x cubed there, plus x to the exponent of a 4. So that means in the simplification process of expansion of brackets, depending on the method that you're going to use to expand your brackets there, you're going to have something like this at the end. So you are supposed to know this expansion of these brackets. After that, what we need here is to integrate. So the volume with respect to x is gonna follow up this integral that we are given here. That is, we're gonna have pi into. So remember the integral, we add 1, so it was going to be 9x to the exponent of 3 over a 3, which is a 3. This was gonna cancel, and this will be 3. So we're going to have 3x cubed. All right, the minus, so this is the same here. This is gonna have a minus here. So this is, we add a 1 on the exponent, so it was going to be 6x to the exponent of 4 over a 4. So you can write it like this, 6 over 4, but if you reduce this 6 over 4 on your calculator, that is 3 over 2. So this is going to give us 3 over 2x to the exponent of a 4. Which is the same concept here. We're going to add the last part. All right, this one is just a single term. Let's add 1 on our exponent. So that will be x to the exponent of 5. We divide by the new exponent, which is what? Which is 5. With our limits from 0 to 3. That is what we have. So meaning we have our volume, upper limit minus lower limit concept, guys. That one is not going to change. So that's the volume with respect to x was going to be pi for the upper limit, which is 3. Wherever there is an x, gonna put 3 minus 3 over 2. Wherever there is x there, we're gonna have 3 plus wherever there is x, gonna have a 3. All right, so this is for the upper limit minus the lower limit. By just looking, guys, that's a 0 there times a 0. That's a 0 as 0 there. So meaning to say there is actually nothing that we have here. That's just a 0 there. All right. So that's it. We are going to have our volume. So if we were to simplify properly on this whole part of this bracket here, we were going to have something like 8.1. All right, so according to my calculations, they got 8.1. Then if I multiply this 8.1 with pi, I'm going to have something like 25.447 to 3 decimal places. That is cubic units. Remember, that is the volume. That is the concept of the volume. So what are you given in the first? This is the major part. The volume is for x. The strip there is for x. So it means I'm going to use the disk method. And the disk method is the one that we are using. So here, this one is just a repetition from our N5. Disk method, that method that you're doing, that we're using in N5, that one, we are not talking about that to say this is disk method because there was no other method to compare with. So we're just saying calculating volume, but we're using the disk method. So let's see this other question that you're given there on this same part. Remember, we've got two things here. After this sketch that we have, I think here I can even minimize this. I can even remove this so that this board does not drag the way that it's doing now. As you can see, guys, it's just dragging a little bit. Let's just hope you will be able to finish. All right. There on the B part, they need the volume that is rotated about the y-axis, which is Vy. This time, on the same diagram. So it's like this. Maybe it's an exam type of a person. You're under exam. They're not going to ask you two questions like this. If they ask you disk method, is fine. If they ask you a shell method, is fine. So they will give you a diagram. Draw this, you have presented, you have drawn this, everything, you are done. Then they ask you now to calculate the volume rotated about the y-axis, knowing fully that what you have just drawn has nothing to do with y. But they are asking you to calculate a volume corresponding to y. But the strip that is there is for x, or the limits that are there are for x, which is something that mathematically we have a confusion of, or there's something that is weird about that. Whenever you notice that happening, that is the shell method. So like I said, don't worry about the strip, represent it. The volume, it follows that. Don't worry about that. The volume, it follows suits the strip. So if the volume is for y, but the strip is something else, is for x, you know that you will use the shell method. It can be calculated. So in most cases, when it is an exam type of a question, we have a tendency of worrying. We want to have a strip for y because they are saying the volume is for y. No, it's not like that. Use the limits that are there. It can be like that by coincidence that it's a definite thing that the limits that are there are for y. It's an advantage when it is like that. It's an advantage. You use your disk method. The volume is for y, the strip is for y, the limits are for y. You just use your disk method. It's an advantage. But not to say that the volume is for y, the strip for x. No, that one is now shell method. So we concluded and say that if you're calculating the shell method for Vy, these are the formulas for the shell method. So this one is going to be given now. You see this at disadvantage. I mean, okay, this one is fine like that. And Vy is this. So you're going to take this one for Vy, which is our shell method. Remember, we are calculating Vy, but having the strip for what? The strip for x. So it follows that our Vy is going to be given as from the strip of x. So it's going to be 2 pi, the integral of xy. So the formula, if you check, is the same, the product of xy. So it is you. We need to know what exactly it means here when you say the product of xy. With respect to x, it means this x, there's nothing to be substituted with. But this y here, it is supposed to be written in terms of what? In terms of x. So this y is our function of what? Is our f of x, which is this one, in terms of what? In terms of x. So let us substitute this and see. So it means our volume with respect to y is going to be 2 pi, the integral. As you can see, guys, with respect to x, we are using the limits for x. The volume is for y, but the limits are for x. Take note. So that is it there. So this is going to be y there. Y is 3x minus what? 3x minus x squared. So this will be 3x minus x squared with respect to x, as you can see on our diagram, the strip for x and the limits for x. So you'll be wondering to say, how? So as long you apply this method, you are calculating the volume for y. You are calculating the volume for y, but using limits for x. That's shell method. So if you check, the formula is totally different. It's totally different. Know your formulas. So there, what can we do to find this volume? As you can see, after this is just your normal simplification, expansion of brackets so that you can be able to integrate. So that means here we're going to have x times this, which is going to be 3x squared, x times x squared, that is x to the exponent of 3 with respect to x. So we are integrating each and every part. Remember the concept of your integration. We add 1, so it was going to be 3x cubed over 3. So this was going to cancel at the end. So that is Vy in this case was going to be given as 2 pi into x cubed. So you can see this cancelled, minus, this is just a single term, just add 1 there. So that will be x to the exponent of what? Of f4. So if we add 1, that will be x to the exponent of 4 over f4. And the limits from 0 to 3. That is it. We are working with something for x, but the volume is for y. So if you're doing that, you are using the shell method. So Vy is going to be 2 pi. We substitute our limit, upper limit. When x is 3, that will be 3 to the exponent of 3 minus 3. So that will be 3 to the exponent of 4 over 4 like this. So this is it. As you can see, that's a 0 here. That's a 0 there. So meaning to say there is nothing that you're having here. So that's it. That is the volume with respect to y. So if we were to simplify properly, this was going to give us 2 pi times 6.75, which is something like 42.412 cubic units. That's it. So the limits that were being used are for x, but we are calculating the volume for y from the limits of x. So if you can be able to understand this, the difference between this, you are done. The difference between where this disk method can be used. So we use disk method on this one because the strip was corresponding. This one, it is using a strip for x, but the volume for y does not correspond. So it's shell method. But these ones, they were corresponding. Volume for x, it was the strip for x. So there we are going to use our disk method. Sorry for that, guys. I'm still having this in mind. So you're going to have our disk method, the strip for x, the volume for x, the strip for x. So if it is the strip for y, it must correspond to the volume for y in order for you to use the disk method. Vy, dy. But the moment now you see Vy versus dx, that one does not correspond. That's where the shell method is used. That's where you apply your shell method. So I just hope we are together. I just hope we are together, guys. You see, this board now is a problem. I just have to remove some of the pages so that it can allow us to finish this class, because the way that I'm feeling now is like we might not be able to finish this because of this board. Anyways, let's see this other part. This other part here, we're just gonna see where it is applicable to use the best method. Now you know how to use your methods, depending with how the strip is given. Does it correspond or not? Determine the volume of the solid. There's a solid that we have obtained when the area between the curve of y is equal to half of ln x, the lines y is equal to 2, y is equal to 3, and the y-axis rotates about the x-axis. So this one, we want to leave it for now. This is the question for volume, this one. When it rotates about the x-axis, it means you are calculating Vx, the volume about the x-axis, you are calculating Vx. So that one is not for us. We will see it later on. Let's have the diagram first and see what we have from the diagram in terms of the strip and all those things. So here we are given the graph of a ln. A ln is a log. Remember, the normal presentation of a log or a ln x is something like this. That's it is we do not have a ln of a 0, so it is an asymptote. So it starts from these points increasing as x values are increasing, y will be increasing sharply. All right, so like I said, these functions, guys, we just need to have a basic understanding of how to sketch each function from our N4. think it was n4, yeah. So meaning to say our function at the end was going to be like this. We are going to have something of this nature. All right, so I just need to be approaching. So something like this, yeah. So it will be like it want to is so it's like to approach the y-axis, but it won't because y-axis is the asymptote. So remember, the logarithm to be a 0, it must be at 1. Logarithm of 1 is equal to 0. So this point is at 1. So if we check, it was going to be very difficult for us to use this function of a half ln of x. If we had given the limits, but according to, I mean, if we had to choose the limits for just we are choosing for ourselves, and also the region to be taken, we were going to choose according to what we're given and the boundary. That is the major thing for you. You don't consider to say, okay, I have something like this, so I'm going to have something like this. No, it can be like that, which is true. But according to what you're given after drawing this, they are saying here, this function is supposed to be obtained between the function, the lines y is equal to 2, and y is equal to 3, and the y-axis. All these, all this information that we are given there is to locate the position of the area to be rotated to give us a volume. Y is equal to 2, which is, remember, y is equal to, like in the x-axis, that's where y is equal to 0. So it means maybe this is 1, 2, 3, 4, and so on. This is a sketch, guys. You're not supposed to think much there. So that is maybe at point 1 there. This is the equation of y is equal to 1. So meaning to say, in the y-axis, this is at a point where y is equal to 1. If it is y is equal to 2, at a point 2, just like that. So in this case, guys, we need y is equal to what? Y is equal to 2 and a 3. So I'm just going to take this one as y is equal to 2. So this point will be at 2. Then y is equal to 3. Let's say this is somewhere here. All right, so this is just a horizontal line straight to the graph. So straight to the graph, this is the equation of y is equal to 3. So it means y at that point is a 3. So they are saying this is supposed to be between this graph, this line, and the y-axis is supposed to be there. The y-axis is there also here. So which region is bound? You see that the region that we are talking about is this one. Between the curve, y is equal to 2, y is equal to 3, and the y-axis. That is where the region that that's where the area is that we are going to rotate. So according to this region or this area that you're supposed to rotate this one, what are the limits that are bounded by the graph and all this? The limits there are for y, not for x. We don't have anything for x here. There's nothing here between the curve. It's open here. There's nothing. The curve is this is your curve, this one. So between, you are considering what is bound between this is bounded this side. Here it's open. There's nothing to be considered. It's just an open space. So it means, according to this diagram, according to this, the limits that we have for y, the representative strip is best for y. I said, don't look into the question, look into the diagram. What is best on your diagram? It is best for us to have the representative strip for y, since the limits that we have are for y. So like I said, y, we can just take our limits as c and d. All right, so meaning to say y is greater than or equal to from 2 to what? From 2 to 3. These are the limits for y. So the strip is for y. So, but the question is, Determine the volume when all this rotates about what? We now answer the question for volume now. If it rotates about what? About the x-axis. About the x-axis, which is Vx. That one, don't worry about it. It follows suits your volume. Your strip. Don't even worry about that. They are asking you to calculate the volume for x. What are you given from the diagram in terms of the limits or in terms of the strip? The representative strip is for y, as we can see here. Can we use disk method? No. Automatically, no. It means we are left with the share. Because disk method, it must, the volume for x must correspond to the strip for x. But look what is happening. They want us to calculate the volume for x. But on our diagram, the strip there is for y. These two, they don't correspond. So in that case, you use the shell method. What does it say? What does it state? The strip, the volume for x, the strip for y. Let's go back to our shell method. We need the volume for x. The strip is for y. So like I said, these are the limits C and D. Can we just correct that part? Yes, yeah, they can write A and B, knowing that it's the limits for y then. But it's best that you just know, guys, limits for y, it's what? It's C and D. So meaning to say, our Vx, we saw that the formula there is supposed to be given as 2 pi, the integral of xy, with respect to what? With respect to y. Vx dy, they don't correspond. That's shell method. So the limits are for y. That's, I'm just going to use C and D because the limits are for y, C to D. So this one is just between the curve and the y-axis, so there's nothing to be done. What we need is to make adjustments on this formula. The x is supposed to be in terms of what? In terms of y. So this x here is in terms of y. So to be in terms of y, it means it's a function of y. Y it's already there, it's with respect. So this one, there's nothing to be substituted. So the question is that, where can we have x written in terms of y? From our original function, y is equal to a half of ln of x. So this x can be written in terms of y. So what can we do? We can remove these 2 by multiplying by 2 here, multiplying by 2. So this is cancels 2 times y. That's 2y is equal to the ln of x. Remember, I say the ln of x is same as the logarithm of x in base e. So what does it mean? It means that if we take this to our exponential form, x is equal to the base of e to the exponent of the answer. That is e to the exponent of 2y. Changing from log to exponential form. So meaning wherever we see x in terms of y, this is our x in terms of y. That's our x in terms of y. So what are we going to do? We are going to substitute this information that we are given now. Vx is 2 pi, the integral of this. So the limits, like I said, are for C and D, which is for y from 2 to 3. These are the limits of y from 2 to 3. So the x in terms of y there is this e to the exponent of 2y. So this y is just going to remain as it is because it's already a y function. But this x, when written in terms of y, it gave us what? E to the exponent of 2y. With respect to y, this can be integrated and we can find the final answer from there. That's it. That's it. Just like that. So you just have to be careful. How are you given the information? So let's integrate this. Which method can we use? As you can see, there's a product of two functions there. An algebraic and exponential from our normal integral. We are now back to question number 2. We are now back to question 2. That question of integration, if you're given something like this, which integral do you use? If you check, this one is by parts. It's a product of two, exponential and algebraic. So from our by parts, we actually know that it was supposed to be like this, the integral of f of x, this and that. But now it's no longer f of x, there's y there. So it's going to be the integral of f of y, g prime y dy like this is equal to f of y. All right, let me just see if this is equal to f of y times g of y. You see, guys, this thing of used to work with x. So this is gy minus, it was supposed to give us the integral of f prime x. So it is f prime y gy like that. So this is it. It's just the bypass method that we are used to, only that we have to write this in terms of what? In terms of y. So, and I also said it is best that if you are dealing with an algebraic and exponential, if you still remember from both introductions, it is best for us to choose an algebraic to be our f of x, which is in this case, it's our f of y. So if we choose our f of y to be the algebraic, which is y in this case, what is going to be its derivative? The derivative of f of y with respect is going to be 1 with respect to y. That's a 1. Just like the derivative of x with respect to x, that's x. The g prime y is the one that is remaining, which is g prime y dy, which is the remaining part of this part of our integral, which is e to the exponent of 2y with respect to y. Integrating these both sides gives us gy, which is the integral of e, guys. Remember, it's e to the exponent of that same function over the derivative of this. It's a linear function, so the derivative of 2y is 2. For integration, you divide. Derivative, you multiply. But integration, you divide. So this is the information that you're going to need to integrate this. This is the information that you're going to need to integrate this. We need by parts. So meaning to say, our Vx from this is going to be 2 pi. They're going to have a lot of things there. So it's going to be 2 pi. We can just integrate this. So this is the one that we're having. So it's going to be f of y times g of y from our by parts. That is f of y, which is y in this case, times g of y, which is this. So it's a product of these two. So this one is just same like ye to the exponent of 2y, everything over 2, minus, in this case, so what are we supposed to subtract? We're supposed to subtract the integral of f prime y, the first derivative, which is 1. All right, that's our f of y, f prime, times gy. Our gy, we got this, which is e to the exponent of 2y over 2. So that is what you're going to have in that case, with the limits from 3 to 2. So meaning to say, this is not yet simplified because we have to integrate this. Remember, by parts, guys, after subtraction, this one is supposed to be integrated. So we have to integrate this so that we have our final volume expression. So this is going to be 2 pi into this. So guys, here I'm just going to combine because we end up having a lot of things, unnecessary things actually here. You were going to take the half outside. So it was going to be like this. I want you to see something. It was going to be like this. If you take the half out of the integral, it was going to be a half. So it was going to be minus a half there. But I'm not going to write it. I'm just going to write the answer. It was going to be minus this half. Then you were going to be left with the integral of e to the exponent of 2y. You have taken this half outside. So you're left with integral of e to the exponent of 2y. But we integrated this before. The integral of e to the exponent of 2y, it gave us what? E to the exponent of 2y over 2. So that is what I'm simply trying to say there. So meaning to say you're going to multiply this at the end. If you integrate this, it was going to be e to the exponent of 2y over 2 times 2, which is a 4. So that was it. You're done. We've integrated this. So there we are supposed to use our by parts. So you see this method, they will follow you up to the last question number 6. N6 is derivatives and integration. So your basics of integration, they are very, very much acceptable in this level of N6. Very, very much acceptable because that is the game. Anyways, after doing your integrals, as we can see, what we are going to need here is to substitute upper limit minus the lower limit as usual. So that's Vx. So as you can see, we were calculating Vx from the limits of y. So that's the shell method that we are using something that is not common to us. So the upper limit being 3, so this is 3 in place of y. E to the exponent, if I substitute 3, yes, 2 times 3, which is 6, everything over 2, minus, it's a 3 here, so it's going to be e to the exponent of 6 over 4. So that's our upper limit, minus the lower limit, which is 2. So this is going to be 2 times e to the exponent of 2 times 2, which is a 4 over a 2. All right, so this you can even cancel 2 over 2, you can cancel them, minus 2 times 2, that's a 4. So it's e to the exponent of 4 over a 4 like this. So this is what you're going to have at the end. So you've got the volume for X given by this part. You have to make sure that you substitute on your calculator properly. But if you fear to substitute like this one, the first one, it was going to give you 504,206 minus this one, it was going to give you 40.949, something like that. So you're going to subtract these two, multiply to pi at the end, you're going to have 2,911,235. This is volume in cubic units. So that's it. N6, it's interesting in terms of like you're working with something that if you know it, like, you know, this is the formula that I'm supposed to use, integrals, only that there'll be a lot of like integrals that you just need. I'm working with this integral, I'm working with this integral, but the idea there, is the same. The volume was calculated using a strip for y, but the volume being for x. And we said it's possible with shell method. It makes that impossible to be possible. Because we're going to be stuck in actual sense. If this method was not there, we're going to be stuck. Like, I need to calculate the volume with, but this one with respect to x. But look at the strip, it's for y. It's for y. So that is how our questions might be given. There's another question which talks about two functions. I think you can have that and close up everything. That will be it. All right, so we're going to try to make adjustments on this one. Like I said, sometimes on the shell method, you might need to have adjustments made depending with the curve or the presentation that you're given. There we are being asked to sketch these two curves that we are given. The first curve that we are given, that is 3a, the first curve is of xy is equal to 2. xy is equal to a, which is, we're talking of what? A hyperbola. That's a hyperbola from our N3, which can be written as y is equal to 2 over x if we divide by x. That's a hyperbola. Remember, a hyperbola, if a is positive, is going to take a shape in the first quadrant and in the second quadrant, in the third quadrant. If a is a negative, you can be given, when it is a negative, it takes a shape in the third quadrant and another shape will be in the fourth quadrant. That's how you sketch a hyperbola. So the other one, it's a straight line. x plus y is equal to 3. So in order for us to sketch this, and also we are asked to show the points of intersection. So you need to calculate the point of intersection in this case. The points of intersection. So at the points of intersection, it is referred that the two functions will be equal in value. Let's start with that. At the point of intersection, the two functions are equal in value. The two given functions are equal. The two given functions are equal at the point of intersection. Only at the point of intersection. So it follows that this function of y is equal to 2 over x must be also equal to the function of here, which is y is equal to, if I transpose this, it's going to be y is equal to 3 minus x. 3 minus x. So these two, they are equal at the point of intersection. So if they're equal at the point of intersection, so this must be equal to this. So 2 over x must be equal to 3 minus x. What am I having? Expand, if to solve this, we can cross multiply, remove the fractions. 1 times 2, which is 2, is equal to x times 3, which is 3x, x times minus x, which is minus x squared. So you can take this to just avoid you have a negative, so it will be x squared. 3x this side, it will be minus 3x. Already there was a plus 2. There was a plus 2 there on the left-hand side. All right, so let's just stop, guys. You're gonna win. You see this spot. All right, there was a plus 2 here on the left-hand side. That's equal to 0. So if you are to check, we can apply our factorization method. You can also use the formula. If you are someone who is used to the formula, just use the formula, it's fine. That's 1 here, factors of 2, which gives us -3. That's -2 and -1. If you multiply this, you get a +2. If you add this, you get a -3. So that's x there. -2, -1 is 0. So one of these brackets must be 0. So x will end up being 2, or x will be what? X will be a +1. So at the point of intersection, remember, these two graphs are equal. So if x is 2, you can substitute in any of these equations. Y is equal to 3 minus x, or y is equal to 2 of whatever that you're given. So substituting into the equation, y is equal to 3 minus x. If x is 2, substitute 2 there, y is going to be 1. If x is 1, we substitute 1 here, y is going to be 3 minus 1, which is a 2. So that's the point of intersection. When x is 2, y is 1. That's a point. And the other point, when x is 1, y is 2. When x is 1, y is 2. So these are the points that we are given. These are the points that we are given at the intersection of the two graphs. The two graphs, which graphs are you talking about? The graph of, okay, so this one, I think you understand where it came from. Just equate your graphs, this and that. So you said at the point of intersection, we've got 2, 1 and 1, 2. These are the points of intersection. All right. Let us now take these points of intersection to sketch our graphs. There are two functions to be considered. They're a hyperbola, like I said before, and a straight line, a linear function. So for a hyperbola, you just need to know the shape of a hyperbola. If this is a positive, we're going to have something like this. In the first quadrant, it'll be tending as if it is to approach or to reach the x-axis, and the y-axis, something like that. Also, in the third quadrant, something like this. That's a hyperbola. So this is the graph of y is equal to 2 over x, or xy is equal to 2. Whatever that you want to write here, xy is equal to 2, a hyperbola. A straight line, which is the linear function, is given also x plus y is equal to 3, which we manipulated in order to suit this equation, and we ended up with y is equal to 3 minus x. So this one, you can just work with the x-intercept and the y-intercept. At the x-intercept, y is a 0. So if y is a 0, it means x is going to be equal to 3. So we've got a y-intercept at x is equal to 3. And the x-intercept, the x-intercept, I mean, at x is equal to 3. Then the y-intercept, we know that x must be a 0 there, which is a 3 also. So as you can see, our graph, it passes through 3 at x and 3 at y. So you can just sketch a line like that, which can enable us to pass through 2 points, guys. Something like this. That's our straight line. It is passing through x, which is 3, and the y, it is passing at what? At 3 also. X-intercept, y-intercept. These are the x-intercept, y-intercept for the what? For the line. But what we need there is not these points, because at the end, sorry for that. At the end here, we need to sketch the area bounded in between. So if you check, this region is not even important. There's nothing to be considered there, because there's nothing, the line is not this side. If it was this side, we're going to consider this side. This is the one in between. So the region in between is this one that we have here. This is the region bounded by the curve and this, by the two curves. And as you can see, according to the two curves that we are given, this is the curve that is on top of this one from the limits of the x. Yes, this is a point of intersection, remember, 1, 2, x is 1, here x is 2. So x is 1, somewhere there at 0.12. So it follows that x is 1 at that point, because this point was 1, 2. This point is 2, 1. X is 2 here. So this is 2, 1. So x at this point is a 2. So in between this region, we can see that the function here on top, the function here below, the limits best indicated there are for x, not this one for y, because it will be, even this one here, it's going to be work again. It's going to work, yes. This one on top, this one below. So we have got these limits on this side of x. So the strip there is something that you can relate to what you're given. But in this case, guys, if you want to have it a normal part, let's take a word for x. If you want to properly see, because this one, you can see that it is above in terms of the y values than this one. The x function, let it be something like this. All right, so that you don't have a mistake there in calculations. So there, let's say having our strip or our limits, that is for x there, from 1 to 2. The question is, we have the limits for x. All right. These are the best ones. That one for y cannot work, guys, because this one cannot cover up that side. No. So this is what we have. We have our function. We are done. Point of intersection we indicated. Let's check the B part. On the B part here, they want us to determine the volume now of this solid obtained when the area enclosed by those two functions now, enclosed by the two curves, rotates about. It rotates about what? The y-axis, meaning to say we need to calculate Vy. So the volume, yes, it's for y. Yes, the volume is for y. But according to our diagram, the strip is for what? The strip is for x. I think you saw that. The strip there is for x. But they need us to calculate the volume for y. So which method do you use when the strip and the volume, they do not correspond? Volume for y, strip for x. That's where the shell method plays a role. So that's it. Our shell method can be placed into consideration. So using our shell method to calculate Vy, as we saw from that formula, is not going to change. they are going to give you that formula. Sorry for that, which is, sorry for that, 2 pi y into this. This is the formula that will be given. I think we saw that the integral of xy. That is what they are going to give you in that case. Well, only that vy, they strip for x, so they strip for x there, meaning to say the limits are for x from a to b. It is you who is supposed to make adjustments, like I was explaining here. It can be a condition that the limits are for x. It can be like that. The limits are for x, but you need vy. So you're going to use 2 pi x into, you have to subtract y1 minus y2, which is the one on top minus the one below. So as you can see, guys, everything is there. So this y there, we're going to make adjustments. So it will be 2 pi, the integral from a to b. The x is representing this with respect to x. But this y is for the function that we have. So we're going to have the one on top, as we can see, the one on top in this case above is the line according to the region. So is the one for the straight line. For the straight line, y1, y was equal to, we made this to be the subject, it ended up as 3 minus x. From that x plus y, we transposed this and it was 3 minus x. So y2 is this one below this one, that is this one, as you can see, it is one that is below in terms of the y values. So that's going to be a y2. So that is, we're going to subtract there. The y there simply means that we are not doing. So that is the case. Y is not, there's nothing there. It's not y squared. It's just the y, but you have to consider to say it's in between. So I have to subtract. So you're just subtracting your y values as they are, y1 minus y2, but just that they are supposed to be written in terms of what? In terms of x. So everything that you're supposed to have here is supposed to be in terms of x. So this will be 2 pi into the integral of this. The limits are for x. So the limits for x within the intersection where the graph is between the graphs, that is from 1 to 2. X, like I said, it's already with respect to x, so there's no substitute there. Then we're going to take y1, which is the graph on top, the straight line. That is 3 minus x minus y2, that's a hyperbola, which is 2 over x. So there is just a single function. I mean, a single term, we just subtract 2 over x. With respect to x, we are going to, guys, this is, what am I doing here? This is vy. All right, I have to finish now. Almost done. So this is it, guys. We are going to expand this so that we can have our integral. As you can see there, we are almost done. X and 3, that is going to be 3x. If you multiply x and 3, that will be 3x. X and minus x, that will be minus x squared. X and minus, so this is like this, x times negative 2 over x. So this will cancel. You remain with what? A negative 2. So that's a negative 2 with respect to x. With this, we are done. We just have to integrate each and every part. Then after that, substitute your limits. So vy is going to be 2 pi. If we integrate, this will be 3x squared, just 1 already. So 1 plus 1, that will be a 2. So it will be 3x squared over 2 minus, if we add a 1 here, that will be x cubed. So that's x to the exponent of 3 over 3. Remember, a constant, you just multiply by x. So that's it. Our limits from 1 to 2. Lower limit to the upper limit. After you have integrated this, you can substitute your limits in that case. All right, so let us just substitute our limits. Vy is going to be 2 pi into upper limit where x is 2, so that will be 3 by 2 squared. All right, so this is 3 by 2 squared over 2 minus in place of this, so that will be 2 to the exponent of 3 over 3 minus 2 times 2. So that's our upper limit minus the lower limit. That's a 1 here. So 1 to the exponent of any number, it just remains as it is. So it's 3 over 2. Just going to work with 3 over 2 here. 1 over 3. There's a 1 here, so it's just minus 2. All right, so that is for the lower limit. So that's it. You were going to simplify this. If you were to simplify this properly, you were going to obtain something like 2 pi into, the first part was going to give you negative 2/3. If you're simplifying each step, then the other part was going to give you negative 5 over 6. So that's a plus at the end. If you check minus, minus, that's a plus. So if you add that, that will give you a 1 over 6. So that's Vy is 2 pi times 1 over 6, which is going to give us 1,047 cubic units. This is volume. So as you can see, the simplification thereafter, it is something that we might be used to. But before that, what to be used? Are you understanding that? That is the major part. Are you understanding that? What is to be used on the previous part? The strip is for X, but they need you to calculate the volume for Y. What are you supposed to use? What are you supposed to use? So be careful about that. These are the typical questions that we are going to have. We just need to work with more questions. These are the formulas. So in our questions revisions, let's also try to do as much questions you might see where this formula might need to be applied. But I think I explained everything that you need there on the basics of your methods like the disk method, the shell method, and also the formulas. These ones are for the disk. These two are for shell method, but you can make adjustments when they are found between two given curves like this. For volume for disk method, that one I'm not worried about it because it is the major method that we had in our N5. That is what we had in our N5.